This is a kind of a summary paper that looks at how climate is changing in terms of natural modes of variability like El Nino and some teleconnections and various processes like ice cover and so on, and tries to argue that models are improving our understanding and also trying to provide reliable projections. And I will just report it as is because there are a lot of papers looking at all the biases in the models and uncertainties in the projection. Especially they talk about the monsoon, and monsoon is not being done very well by the models when you look at the historic trends that are actually in the data versus what the models are doing, and that relates to a more complicated problem of impact of aerosols that we will briefly mention. I will not go through every section of the paper, but just try to highlight a few points because I think the paper is interesting enough to listen to. The reality of human-induced climate change is unequivocal and exerts an ever-increasing global impact. Access to the latest scientific information on current climate change and projection of future trends is important for planning adaptation measures and for informing international efforts to reduce emissions of greenhouse gases. Okay, this is understandable. Identification of hazards and risks may be used to assess vulnerability, determine limits to adaptation, and enhance resilience to climate change. Very good. This article highlights how recent research programs are continuing to elucidate current processes and advance projections across major climate systems and identifies remaining knowledge gaps. So that's the main purpose. Key findings include projected future increases in monsoon rainfall. This is where the problem is in terms of models being inconsistent with the history as well as historic trends as well as dynamically inconsistent for the future. Nonetheless, these result from a changing balance between rainfall reducing effect of aerosols and rainfall increasing effects of greenhouse gases. So they identify some of the complexities. Also, a strengthening of the storm track in the North Atlantic, an increase in the fraction of precipitation that falls as rain at both the poles. As warming happens, we are likely converting snow into rain, an increase in the frequency and severity of El Nino Southern Oscillation events. This is also very tricky because models have not been able to explain what has happened. You can always argue that the sample is not long enough in terms of the historic records of El Nino, but they look for certain consistencies in the models as they go forward and draw some conclusions in terms of an increase in the frequency and severity of El Nino Southern Oscillation events. But not all models agree. Okay, along with these come the changes in ENSO teleconnections to North America and Europe. This is already observed, and an increase in the frequency of hazardous hot humid extremes. So it's not just that temperature is getting warmer and heat wave duration, intensity, frequency and scale are increasing. It's also that humidity increases as you increase temperature, then exponential dependence of humidity on temperature, and as humidity increases, our body's ability to get rid of the heat by perspiring begins to become less effective, and that's what hot humid extremes are. These changes have the potential to increase risks to both human and natural systems. Nevertheless, these risks may be reduced via urgent science-led adaptation and resilience measures and by reduction in greenhouse gases. That's a very generic statement, but nonetheless it's important and always good to remind ourselves. Let's just read off the key points so that if you want to leave the podcast at this point, you can do that. Monsoons are expected to increase in intensity in the future as aerosol emissions abate and greenhouse gas forcings emerge, increasing risks of floods, landslides, and reduced agricultural yields in affected regions. The point is that right now it's argued that aerosols are responsible for solar dimming, cooling the land. India is cooler than rest of the regions around, for example, and hence reducing the ocean-land temperature contrasts and reducing monsoon as observed. But in the future, as we take climate action further, aerosols may decrease, and we may get back to increasing the monsoon as we expect, because land has lower heat content and can warm rapidly compared to the ocean, which should give us a stronger monsoon. Okay, that's the idea. But you realize that risks of floods, landslides, of course it's true, but where? So we need really local information, which we still don't have. Very high resolution climate models have recently highlighted potential strengthening of the storm track into the northwestern Europe, risking an increase in landfalling extreme storms likely to cause high winds, flooding, and threats to infrastructure. So as tropics expand and warming continues, there is some evidence that the storm track over the Atlantic gets stronger coming off of the North American continent, and then you have more storms coming into northwestern Europe, so UK and the rest of them. An increasing fraction of precipitation will fall as rain rather than snow over both poles in the future, potentially destabilizing melting ice and amplifying sea level rise. Well, you have to remember, sea ice will not do that, but obviously if glaciers begin to melt, land ice begins to melt, sea level will rise. El Nino Southern Oscillation events, which cause floods, droughts, heat waves, and wildfires around the world, are expected to increase in frequency and severity in as little as 20 years. This is something that you must follow up on, because this is not really so well understood, and the models have all kinds of issues, so whether models can be trusted on this remains open. Temperature extremes are increasing globally, true. Impactful events often combine with heat and humidity, true, thereby significantly affecting sectors such as agriculture, negatively impacting crop yields, reducing the ability to work outdoors, and increasing mortality in vulnerable populations. So again, very general, true points, but local scales are needed in terms of where actually these adaptations can happen. Okay, so what is the motivation? Human-induced forcing of climate change, principally due to increases in atmospheric carbon dioxide and other greenhouse gas emissions, is unequivocal, and the climate will continue to warm until net zero emissions are achieved. While actually it will continue after that as well because of cumulative carbon. Even if CO2 emissions ceased completely, global temperature would remain elevated for many decades, and it would take centuries before atmospheric greenhouse gas concentrations return to the pre-industrial levels via natural uptake processes. Assessing the likelihood of different levels of global warming over the coming decades is important to inform efforts to avoid dangerous climate change. So these are generally very general statements, but this article builds on recent comprehensive IPCC reports and synthesizes recent studies from diverse geographic areas ranging from the equator to the poles. A complete synthesis of all aspects of regional climate change is not possible given the constraints on the length of this article. Hence, we focus on a few key areas, and I will be even briefer and skip most of the details. Obviously, the projections are based on scenarios, so assumptions underpinning the shared socioeconomic pathways used to characterize different levels of future global warming and climate change. So there are shared socioeconomic pathways 1, 2, 3, 4, and 5. So the scenarios include things like a world of sustainability focused growth and equity. So it's a very safe pathway for hopefully staying below 1.5, but it's fairly obvious that we'll exceed that. And then you have middle of the road, fragmented world, ever increasing inequality, and fossil fueled world. And the challenges to mitigation will be low, and challenges to adaptation will be low in this most benign scenario. Will we be able to manage it still? Well, let's hope so. Middle of the road has moderate challenges to both, but if you go into fragmented world with regional rivalry, both challenges are high. World of ever increasing inequality may leave mitigation challenges to be low because you have, let's say, put a lot of effort into technologies to do carbon capture and other mitigations, but changes will keep happening, so adaptation challenges will be high, and in the fossil fuel you have both challenges being high as well. So there are different ways in which you get to bad situations, but nonetheless. So assumptions underpinning the previous set of concentration pathways, representative concentration pathways, I won't read into it, but this is important because 2.6, 4.5, 6 and 8.5 correspond to the radiative forcing compared to the pre-industrial level. That's the additional amount of input of energy or imbalance at the top of the atmosphere, or the additional energy we are trapping by 2100 will be 2.6 in SSP1, 4.5 in the middle of the road, 6 in the third one with inequality, and 8.5 with, which is called business as usual, where we just keep burning fossil fuel and hope that carbon capture will save us. So the range of temperatures out in 2081 to 2100 will be 1.5 to 2 in this case, but we are already butting up against 1.5, and there are lots of uncertainties in these things anyway, so you will have strongly declining emissions. The next one will take us to 2.5 to 3, to 2 to 2.4, and 5. So why is this lower? Because you have stabilizing emissions, whereas here you have slowly declining emissions. There are many details that matter why this is lower warming than here, but I won't go into those details. Jumping ahead, the results reported here use a range of different approaches to assess the signal of climate change. Some compare changes in different SSP scenarios, while others compare changes at different warming levels, or simply assess the largest global warming scenario to maximize the signal to noise ratio. So if you do business as usual, changes are so huge that you can be statistically confident about those, and then you say, well, we will not get there because we are already doing something like renewables and so on, right? So climate change signal against the background of natural internal climate variability will be very clearly identifiable if you go with the top worst scenario. So in general, we do not assign likelihoods to different warming levels or scenarios, but rather seek to assess confidence in signal based on our understanding of how the climate system works. So I will jump right ahead and also look at just mention how low frequency climate variability is considered. There is a lot of details, each like El Nino, polar ice caps, monsoons, and so storm tracks, El Nino, etc. are considered in words as to what has been happening and what is expected from future projections. They are generally kind of a summary of the summary of IPCC with some additional points that have come after the synthesis. So it's a good paper to read, but I'm not going to summarize all of it. Low frequency variability, i.e. anomalies that persist for more than one season in atmospheric circulation in the Atlantic sector, appears to be underrepresented even in the latest climate models. Similarly, signals of decadal change in and around the Atlantic sector appears to be underestimated in current climate predictions. This means that uncertainty in multi-decadal climate change around the Atlantic basin is also likely to be underestimated, and multi-decadal variations, for example, in winter storminess, could be greater than estimated by current models. So we kind of say where we are going, and then we say, but we may be underestimating everything. Related to this is the question, how robust are current projections of ocean circulation changes and their impacts on mid-latitude storms to an increase in model resolution? Models, because they have to run for multiple centuries in these scenarios, they are necessarily coarse resolution because of computational burdens, but some high resolution simulations are made for some periods or sometimes for the entire period and so on. So you need to understand the impact of resolution. Early experiments with higher resolution ocean models forced with some winds and fluxes from somewhere. Early experiments with higher resolution ocean models suggest the potential for greater decadal variability and greater levels of climate change and climate variability than found in the low resolution models. Atmospheric resolution may also play a role in as transient eddy feedback, crucial for maintaining storm tracks, and amplifying changes may increase at higher resolutions, further exacerbating trends beyond current predictions by lower resolution models. A lot of technical words there. If you don't understand, you can skip, or if you understand, you know that mid-latitude there are baroclinic instabilities which generate eddies, storm tracks. We have to accomplish northward heat transport, which happens by the atmosphere through these eddies, and those have a feedback during the warming. And there are many ways to think about the details, but we'll skip that here. Let's just run through some figures. Here we are, the historic period in the observations in the black line, coming up to about 2023 or so, 24, when this paper was published. And you have CMIP 5 simulations which took us in this gray range, and then CMIP 5 ensemble mean of all the model ensemble is members you create by doing simulations that differ because you perturb some initial condition and so on. So you see that models do reasonably well in capturing observed trends, not these ups and downs in observations are internal variability, and there are details as to why the models do not capture the internal variability, which is what we talked about before, and also mentioned it as large ensembles doing a better internal variability in the previous podcast. Nonetheless, you see that the discrepancy adjusted mean projections take us here, whereas the ensemble mean of CMIP 5 take us there. So this is not even using CMIP 6. So this paper is using older output. Probability of global surface air temperature change being greater than 2 degrees C from 0 to 100. We went from 1900 to 2010 or so, or maybe this already, 2023 or so, and then it jumps up in the models. So that's relative frequency from 37 CMIP 5 simulations, relative frequency from 10,000 simulations out of the posterior predictive distribution. So there are ways of doing taking outputs and making predictions, and then we lower the probabilities out to 2100 basically. So temperatures relative to long-term means over periods. So there are some details here that I won't read, but you can take what you want out of this, or you can go and read the paper, because I find these to be useful, but this is all model world here as you go into the future. And the main point to remember is that out from let's say the current year 2024 to about 2040 or so, all the uncertainties are in the model, internal variabilities and uncertainties, biases, whatever you want to call them. But once you go beyond about 2050 or so, all the uncertainties come from scenarios, all those SSP and RCP scenarios we saw. So I'm not even a big fan of doing these sorts of projections where we have hardly any control on the uncertainties. Okay, so this is again looking at global mean surface air temperature over time from climate model, one of them UKSM, that's the Earth system model, experiments in which all anthropogenic forcing were held constant at the level they were at in the year of branching off in 2020, 25 and 2040 from the parent shared socioeconomic pathway scenarios. This includes constant concentration of greenhouse gases and constant emissions of anthropogenic aerosols and their precursors. So basically various ways of doing it and looking for some kind of a transient sensitivity to see if we freeze the emissions at some level, where will we reach in the coming centuries? How much do we even trust integrating out to 2500? Well, already by 2100 the uncertainties are quite bad. So if we keep integrating, what will happen to land use, what will happen to forests, how warm will be oceans, what will happen to carbon cycle. So there are lots of uncertainties in these things. Nonetheless, looking at June to September air temperature difference between present day conditions, so that's 1979 to 1999. So these are for different scenarios. This is for SSP 2.6 minus historical, so you can see that it's capturing some of the things pretty well for 2035, 2060. We are seeing that the Sahara and Mediterranean, Middle East regions are already warming. Obviously, it gets much worse as you go into the worst scenarios like SSP 3, 7.0. So that's the radiative forcing versus the other assumptions in scenarios of shared socioeconomic pathways. And this is differencing SSP 3-7.0 with SSP 1-2.6, so you know relatively how much worse off you will be if you fail to meet this benign scenario and end up this with this one. So you can again see that India appears to be cooler here, and they have chopped off the higher latitudes and polar amplification and so on. But nonetheless, looking at the monsoon, you can see here the difference between responses show the same but for precipitation. So there will be changes in precipitation for these scenarios compared to the baselines for these SSP1, SSP3, and comparing the two scenarios. So basically what we were saying before, that if aerosols disappear, then monsoon is expected to increase. How much do we trust them? Models have all kinds of troubles doing precipitation. They do temperatures fairly well, but at a regional scale, not at a local scale. They do precipitation pretty badly, and nonetheless we have to just look for dynamical inconsistency between the models to see whether what they say compared to all their biases in the historic period and the current period. Okay, so this is about the ocean. Global mean surface air temperatures over time from climate model UK ESM 1.0 LL experiments, in which all anthropogenic forcings were held constant at the level they were at in the year branching off in 2020, 25, 2040 as before from parent shared socioeconomic pathways, that 7.0. This includes constant concentration of greenhouse gases, etc. So we are looking at resolution impact. So 1/4 of a degree ocean, this is the distance of the Gulf Stream from the coast. You can see that this is tremendously different from the coarser, from the higher resolution. So 1/4 degree is here, historical model and future projections are here. But if you take 1/12 degree eddy-rich ocean circulation, then it's much higher to begin with over the historic periods, and then remains high in this one and goes crashing down here for historical model and future projections. So observations are here somewhere in the middle. Basically, models have issues, and nonetheless you are looking at eddy-rich ocean and what happens over Western Europe, and eddy permitting region and what happens over Western Europe in terms of the December, January, February surface storminess in terms of meter per second. Okay, so this gets much stormier when you have higher resolution ocean, because somehow it's able to do different things in the forced ocean. So what will this mean in the coupled model? We still have to figure that out. I think I'll skip these projections, but basically again, December to January, March to May, June, August, September, November, projections of 21st century changes in zonal mean temperature and zonal winds. So they show coupled model income CMIP 5 ensemble means of time slice differences between 2070 to 2029 in one of the pathways and so on. But basically you see that there are seasonal changes as you go forward as expected, and zonal wind strike, basically you will be looking for, so this is the meridional section here, and you will be looking for how the jet stream and the tropospheric stratospheric interactions change, and storminess, that basically relates to storminess. So you are looking at mean sea ice edge equivalent latitudes, satellite derived equivalent latitudes. So they try hard to compare historic periods to models, and then future simulations, future projections to models, and you can get whatever message you want out of it. But my main message is I don't trust the models so far out into the future. Okay, changes in El Nino, you can look at the teleconnection changes and you can see the different models here. They are very different. Okay, so this star here indicates models with temperature anomaly change significant at 5% level. So one significant model is putting the northern North American El Nino temperature anomaly change as positive, but the rest of them are putting it as negative, and some are putting it at fairly large minus almost minus 2 degree Kelvin or 2 degree C. It's an anomaly, and the red line here is indicating yeah, so basically they are looking at northern North American teleconnection and arguing that models are giving different answers, but you can still get some meaningful emergence of climate signal out of it. Changes in El Nino Southern Oscillation teleconnections, multi-model mean abrupt 4 CO2 minus pi control surface temperature anomaly in El Nino years. Change in surface temperature anomaly averaged over the northern North American region for each coupled model in comparison project CMIP 6 models and the multi-model mean. In the abrupt 4 CO2 simulations, the positive El Nino temperature anomalies are weaker in almost all models across much of the northern North America. The models in B are arranged from the positive to negative temperature anomalies, with red stars indicating models with temperature anomaly change significant at 5% level. What is the red line then? Oh, that's the multi-model mean. Okay, so what do you do with it? Basically know that models produce very different answers and you still want to make sense out of it. So just to kind of close out, from hazards to risks to climate action, in recent research findings described above mainly address changes in the probability of different climate hazards. To properly translate hazard analysis into risk analysis also requires evaluation of vulnerability and exposure, and many of the impacts of these events are multifaceted, of course. For instance, the health impacts of heat depend not only on atmospheric conditions but also on human behavior and physiology and on the built environment. Similarly, damage and human impact from tropical cyclones are the product of relevant socioeconomic and behavioral patterns, demographics, disaster planning and governance, as well as the physical climate event itself. Basically, in the IPCC construct, you say risk is a multiplier of hazard, that's the climate change impact, vulnerability, which is all these things, socioeconomic, demographic factors, behavioral factors, income, etc., and exposure, which again is a part of the system, hospital, access to hospital, population density, infrastructure, and so on and so forth. Consider the global impacts of changes in heat extremes. The ability of 1 billion people to work outdoors will be affected by hot, humid conditions if global warming reaches 2.5 degrees C, 2.5 degrees centigrade, while 100 million people could be exposed each year to deadly conditions if global warming reaches 3 degrees centigrade. As agricultural labor is seasonal, considering only annual changes can lead to an underestimation of the impact of hot, humid conditions on agriculture. These studies, among many others, show how increases in humid heat associated with global climate change can severely affect populations relying on outdoor labor, with a triple threat to health, productivity, and food security. A more comprehensive assessment of hazards, risks, vulnerability, and resilience would allow governments, citizens, and businesses to take the actions they need to adapt to future climate change in conjunction with the implementation of strong mitigation measures to limit GHG emissions. So we are mixing a few things here. If you get information that India is going to get hot and humid and you want to invest money in dealing with hazards, risks, vulnerability, building resilience, and so on, how do you allocate resources unless you have hyper-local information as to the most vulnerable, the most risk-prone places? You can't have enough money to do it everywhere. So it becomes very challenging to actually fund these things and sustain these things. So it's easy enough to say we are going into hotter and humider days and so many people will be affected. But unless you say precisely where resources should be allocated by priority, then it becomes a much bigger challenge. Knowledge gaps and priorities for future research. The climate projections discussed here are important for several scientific and policy reasons: adaptation to existing climate variability and change, and to further changes in the near future, is a recognized urgent priority of the United Nations Framework Convention on Climate Change. Climate hazards are also a key risk to be managed under the Sendai Framework for Disaster Risk Reduction. I have discussed those elsewhere. Adaptation and risk management must be based on the most up-to-date information about current and future climate changes as described here. However, we need to go further to understand risks to human natural systems and the resilience and vulnerability of those systems, communities, and countries to ultimately implement a plan of action to increase resilience and reduce vulnerability. Again, very general statements. If you ask social scientists and go through the literature, you will see that you will really need much more information at scales that matter. Here we are just saying these need to happen. Yes, sure. We address risks in several sections above, but need not go further if your work on climate hazards is to have an impact. Sorry, need to go further, not need to go further if our work on climate hazards is to have an impact. I'm just tired, I guess. Uncertainties in predictions and projections must be accounted for, but cannot be a barrier to action. Sure, the barrier to action is even if the prediction is 100% accurate, if it's not accurate in terms of the location, or if it's not reaching the location, then it will not be very useful either. Much of the scientific focus on mitigation has been on the sensitivity of the global climate to increases in greenhouse gases and other forcing agents. However, global changes are the sum of regional feedbacks. In the case of equilibrium climate sensitivity, these include cloud feedback, surface albedo changes, especially in polar regions, and vertical temperature lapse rate, and water vapor feedbacks. Understanding and quantifying changes in the phenomenon discussed in this article is key for constraining the equilibrium climate sensitivity. I have discussed climate sensitivity elsewhere. You can look it up. If you don't understand, don't worry about it. If you understand, you know what it means, right? Much work in this area has moved from global to regional scales, processes, and equilibrium is not very useful because we are in a transient situation. Another key piece of global feedback on the problem of mitigation is the sensitivity of the carbon cycle to global warming. Anthropogenic CO2 emissions add to the natural cycle of CO2 sources and sinks, and regional climate changes can disrupt the cycling between those sources. A key risk is in tropical rainfall regions, which may switch from a sink to a source, as is already being argued for the Amazon, for example. As for the equilibrium climate sensitivity, understanding regional climate change, particularly in the tropics, is an important component of constraining carbon budgets and in determining emissions to limit warming. Okay, so it's a very broad paper, but I wanted to include it just because it has some big names on it and has some useful information. So you listen to it and decide whether you want to go and read the paper and look at all the references they provide, lots of them very useful, and decide for yourself where you think and where the gaps are. I don't know, I hit pause by mistake, so let me leave it here.